talk, even if we're not too cumbersome. I think it's good just to clear up confusions or address anything that might pop in your head during the talk if it's quick to do so. So I'll be talking about circuit complexity, and this is sort of like an old story that I think has sort of become interesting again, especially within the last week. So just to provide some references, this is, I guess, the new part of my talk is based on joint work with Yale Fan, Andreas Karch, and Shivan Mittal. And this was a paper that appeared last week. And this was jointly posted to the, or was coordinated with another archive posting by Zhongwan Ha and Douglas Stanford, which appeared the same day. And to the extent I mention older results that are work of my own, these were collaborations with Fernando Brandao, Wasim Chemasani, Richard Kung, who's in the audience here, and John Preskel, as well as another work with Michał Horodecki, Marcin Kotowski, and Michał Oshmanitz. And maybe just to also highlight, there's a few places in the talk where I'll sort of secretly use a real breakthrough result by other authors. So I'll just mention that here. So this is very much a theory talk, and I'm a quantum information theorist, and I'll be talking about circuit complexity, but I think the story I'll sort of say at the end of the talk might be interesting for many body physics. So I should tell you what complexity is. The quantum complexity is a pretty well-established notion in quantum information theory. It sort of allows you to, the circuit complexity of unitaries allows you to distinguish what you mean by, some unitary transformation that's hard or easy for a quantum computer, right? What you can do with few gates or what you need a lot of gates to do. And I'll define this more precisely in a few slides. But there's been a lot of recent interest in both the high energy theory community and the many body physics community in the circuit complexity of quantum states, both as a way to distinguish phases of matter. The circuit complexity of ground states has been used as sort of a way to distinguish topological phases, as well as in holography, where the long-time linear growth of black hole interiors in certain geometries is conjectured to sort of have something to do with complexity. But maybe more pertinently for this audience, I generally think that complexity growth is just some universal aspect of real-time dynamics for strongly interacting many-body systems. And this is sort of related to thermalization, quantum chaos, scrambling, growth of entanglement. And the precise relation between all these things is definitely, not clear. And, understanding those relations is a long-term goal of the subject. Okay. But I should tell you what circuit complexity is before I tell you anything about it. So the systems I'm going to be interested in are systems of n qubits. And just to set some notation here for me, lowercase d will always be the Hilbert space dimension, so 2 to the n. And to define the complexity of a unitary, it's a pretty intuitive notion. I'm just going to mean the minimal size of a circuit built from elementary to local gates that approximately implements that unitary. So it's sort of what you mean by like the easiest way of preparing your favorite unitary. It's the minimal number of gates that sort of approximately prepares that unitary. So we're always going to allow some tolerance because we won't demand, exactly implementing some unitary. So I'm going to imagine fixing some tolerance and fixing some universal gate set. And then the idea is you just have some unitary and you're just breaking it down into a bunch of universal, into a bunch of elementary to local gates, say, or k-local gates. And you're interested in the shortest such circuit which does this, right? You could imagine you sort of accidentally wrote down a huge circuit, some path in the unitary group or some path, that gets close to the unitary you wanted, but there could have been a much shorter path, right? There could have been a much shorter circuit. You could have gotten rid of like half these gates, and it still would have approximately implemented the same unitary using the same gate set with the same tolerance. Okay, so we're going to be interested in the shortest such circuit. And I know it's 9 a.m. and I already have a definition on like the third slide, but I think the intuitive notions are sort of, paints the right picture. And just to make it precise, I'll say that some n-qubit unitary has complexity R. If basically you basically take all the circuits which approximate that unitary, and then you just take the one with the shortest depth. Okay, that's how we'll define it. And of course, there's some, this depends on what our notion of distance is between unitaries. sort of behind the scenes, I'll actually be working with the diamond distance of the channels, but that's not important. It's just some notion of distance between unitaries. Okay. The same thing holds for states. Okay, so the complexity of a state, I'm going to assume you start out with the all zero state or some unentangled state. Okay, and it's the complexity of a state is the minimal size of a circuit starting from that all zero state, constructed out of these elementary two local gates, constructed out of your easy gates, your simple gates, which approximates that state. Okay, which approximately implements that state. So again, take all circuits such that when you act on the all zero state, you get a state close in trace distance, say, to the state you're interested in, and then take the smallest one. Okay, so that's going to be the circuit complexity. And this is sort of what we mean by how easy or hard a state is, right? It's really like how, what's the most efficient way I can implement it. Okay. So it's believed, or expected, or conjectured that the complexity of quantum states grows linearly in time for an extremely long time for generic local evolutions. There's a few words here that are definitely the word generic there is doing a lot of heavy lifting, and there's a lot of, I guess, historical baggage you might pin on that term, but maybe for some notion of generic, strongly interacting many-body systems, this is sort of the picture you expect, where the complexity is growing linearly in time for an extremely long time of this time-evolved quantum state. So you're time-evolving it with your favorite Hamiltonian evolution, some quantum circuit, something like that. And notably, it saturates at an exponential time, so far, far after local equilibration, or like all your favorite, entropies, measures of entropy, all your favorite correlation functions have decayed, all your entropies have saturated. So this is an extremely long time process. Okay. And just to emphasize, conjectures are nice and all, but computing the complexity analytically is extremely hard, especially for a fixed unitary. Right, so we can already sort of see this by the definition. I said you have to take all the circuits which implement your state and then take the minimal one, right? How do you, if you construct some circuit which prepares the state you're interested in, how do you know it's the minimal one, right? It seems like some insanely difficult problem where you have to minimize over all circuits, right? You sort of have to enumerate all of them and pick the smallest one. That seems extremely hard. So, it's almost maybe hinted at by the name, but complexity is an extremely complex thing. And it's very hard to compute analytically for any fixed unitary. Okay. Before it'll tell us how to proceed, I'll just sort of maybe give some intuition about why we should expect this shape. We sort of expect that early time collisions should be rare, right? So if you sort of, maybe have two different random circuits of the same depth, it would be very surprising if they sort of collided in Hilbert space. You sort of expect things to spread out sort of fast, and you sort of expect that these collisions only sort of become between, different time-evolved states only become common once you sort of reach exponential depth. Maybe more precisely, if you have some Hamiltonian evolution, approaches from Hamiltonian simulation sort of give you polynomial or linear upper bounds on the complexity, right? If I compile some Hamiltonian evolution that you're interested in into like a circuit, right, that's an upper bound on its complexity. Okay. Why do we expect it to saturate at exponential times? Well, there's only so many states in the space, in Hilbert space. More precisely, there are doubly exponential in n distinct states. So if you just count the number of delta balls in Hilbert space, it's roughly like 2 to the 2 to the n. Okay. And then if you just count the number of circuits, you can prepare of depth t that's also going to be exponential in n. So when you're exponential in t, right? So if you fix some gate set, it's roughly the cardinality of your gate set to the t. It's the number of depth t circuits. So when your circuits are exponential depth, right, the number of circuits is roughly equal to the number of states in Hilbert space. So you would roughly expect that you should be able to reach any state with an exponentially deep circuit. So that's sort of why you expect this saturation. There's not that many, well, there's a lot, but there's still like a finite number of distinct states in Hilbert space. Okay. Any questions about this? Okay. And this is not a talk about holography, and usually when I've given versions of this talk in the past, I've sort of elided over the holography part, but I now more appreciate the utility of holography in sort of studying many-body physical systems. Holography is, from my perspective, is a very good conjecture generator. Right? There are lots of things that I don't know how to see in like solvable many-body systems or in random circuits, and holography is very, it's pretty easy just to come up with all these conjectures about how things work And I think I didn't really appreciate that before, but it's nice because it sort of tells you what might be going on, and I'll sort of come back to this at the end of the talk. But yeah, this holography is some equivalence between theories, quantum mechanical theories with gravity and without gravity. This long-time linear growth of complexity is believed to be related to the long-time linear growth of black hole interiors. Okay, but this is nice because you can sort of, maybe predict features of complexity and then, sit down and try and prove them in some solvable model. Okay. All right, so I already told you that, this is an extremely hard quantity to compute. All right, how do we make progress? One approach is to sort of use complexity theoretic assumptions to make statements about the complexity of a particular Hamiltonian at long times. So maybe assuming some separation of complexity classes, you build some hard problem into your Hamiltonian evolution, then you can say that the complexity must be like super polynomial at exponential times, something like that. I'm going to be taking a different approach, which is just to focus on distributions of unitary evolution. So I'm not going to be pinpointing the complexity of some specific unitary, but I'm going to be making probabilistic statements. And that's sort of the way around. I've never like pointed to some unitary and said that, it has this complexity, or some state involved, prepared by some unitary and says it has some complexity. I'm sort of saying, with high probability over the choice of circuits, right, the complexity is this. And that's sort of the way around. Yeah, a lot of, maybe I wouldn't call them no-go theorems, but a lot of the difficulty in understanding complexity. Okay, so the model I'm going to be considering, I'm just going to basically review the story for random quantum circuits and the linear complexity growth of states. And then I'm going to talk about complexity of subsystems, which I think is an interesting new part. So I'll sort of go through this story a little bit quickly because it's a few years old. And I think we sort of understand the picture now, and I think there's a lot less understood about the complexity of mixed states and subsystems, and that's really what I want to talk about. But I should review the story. So what I want to do is consider random quantum circuits. We've heard a lot about random circuits in this workshop already on n qubits. And here I'm going to be evolving with some circuit constructed of randomly chosen two-site unitaries. Okay, where the evolution of time t is some size t circuit or depth t circuit. And as a lot of you are probably familiar, random circuits are good models to sort of try and sit down and prove things. And what I want to do is prove the growth of complexity in this model. And actually, the architecture and the gate set won't be that important for me. So most of what I'll say in this talk holds for any random circuit, any architecture, any universal gate set, as long as you sort of have a connected enough geometry, as long as your basically underlying interaction graph is connected, and as long as your gate set is universal, everything I'm going to say holds. Most of what I'm going to say holds. But you can ask me at the end if you're interested in that. But yeah, you can just imagine brickwork circuits, 2D circuits, circuits with different universal gate sets. It won't really matter. Okay? And I'm going to try and prove the growth of complexity in this model. Okay, and more specifically, it's nice when high-energy theorists conjecture stuff for you, because then you can give it a name and write papers about proving the whatever conjecture. So there's a Brown-Susskind conjecture. Brown and Susskind conjecture that random quantum circuits of depth t have a complexity that grows linearly in time for an exponentially long time. This is now known as the Brown-Susskind conjecture. And again, it sounds very reasonable, right? You just wrote down the circuit. Like, shouldn't you just count the gates? Shouldn't that be the complexity? But again, the difficulty is how do you know that I couldn't remove a bunch of these gates and construct, sort of approximately implement the same unitary? How do you know this is the shortest one? So again, that's the difficulty. Okay. So yeah, I mean, you can also phrase this as basically that most quantum circuits of sub-exponential depth are incompressible, right? The linear complexity growth is sort of the same statement that you can't sort of compress your circuit too much before it's exponentially deep. Okay. So the way I'm going to attack this problem is using unitary designs. We've heard about unitary designs already a few times this week, but I'll remind you what they are. And then we're going to use designs to prove complexity growth, and then we're going to switch to understanding subsystems of random circuits. Okay, so maybe just a slightly more precise definition. A local random circuit is, again, just what I was saying. We choose some gate set. We're choosing each gate in space and time randomly from that gate set and applying it to some nearest neighbor pair of qubits, right? And, you can just imagine sort of evolving the circuit deeper and deeper, more and more layers, however you picked your underlying architecture and gate set. And I'm going to be a little bit imprecise about, sort of the definition of depth definitely depends on your architecture. So I'm going to be a little bit loose about when I'll talk about it as depth, and I'll always sort of mean depth is roughly size over n. Yeah, I'll be a little sloppy about depth versus size. And again, just to emphasize, most of what I'm going to say holds for any universal gate set and any connected architecture. Okay. Any questions about random circuits? We're all experts? Okay, good. Good. So yeah, we've heard a lot about random circuits this week, and what I want to do is study the complexity of random quantum circuits. And to do this, what we're going to do is just make a sort of first study the complexity of a nice distribution of unitaries called unitary K-designs, which Sagar has nicely sort of gone over various definitions of yesterday. And then what we're going to do is use the fact that random circuits form K-designs to prove something about their complexity growth. So that's basically the approach. So I'll just go through this quickly. Unitary K-designs, basically the Haar measure is the unique left-right invariant measure on the unitary group. We're often interested in moments of a distribution. So given some distribution of unitaries, I'm going to often be interested in how close kth moments of that distribution are to the kth moments of the Haar measure of Haar random unitaries. So I'll give the precise definition and then a picture. So, an exact K-design is basically the statement that the moments are exactly equal. But for general K, very few exact constructions are known and often not necessary. So really all we're interested in is when some distribution of unitaries, its kth moments are close to kth moments of the Haar measure. And the formal way of doing that is you sort of package your moment into this object called the K-fold channel. This sort of, any moment quantity can basically be re-expressed that way. And then we're really interested in the closeness of these channels. There are fancy norms that sort of capture that well. But the key idea is you just have some distribution of unitaries and its moments are close to those of the Haar measure. And there are, too many definitions of what you might mean by an approximate K-design where these moments are close. There are lots of different norms you could choose. I won't get into that. I think also Sagar nicely reviewed this yesterday. Those are sort of relative error notions, and you oftentimes actually need exponentially small additive error, which is a little bit stronger. Okay. More intuitively, a distribution of unitaries, you can sort of think about these as a set of points on the unitary group, and all you're doing is you have some nice moment quantity, some polynomial in the entries of your unitary involving KUs and KU daggers. You have some distribution on the unitary group, could be discrete, so some set of points. You're averaging over those, and you're just saying, okay, this quantity is for any kth moment quantity, any degree k polynomial in the matrix entry, is approximately equal to the same quantity averaged over the Haar measure. Okay, so it's somewhat surprising. Somehow this nice, well-distributed set of points is capturing enough features about the full unitary group up to kth moments. Any questions about K-designs? So they're just nice distributions of unitaries that are sort of spread out enough. Okay. So designs are useful. There's probably too many references on this slide. But they come up all over the place in quantum information theory, sort of classical shadows, randomized benchmarking, state distinguishability, decoupling, and more recently in terms of sort of different notions of thermalization and pseudo-randomness. I guess in the history of designs, like a lot of the results from 10 years ago used like 2 and 4 designs, but I think higher degree designs have really sort of found a lot of really important applications in the last few years specifically. So yeah, designs are interesting. That's the only point I'm trying to get across. Right, so the problem I'm interested in is, given some unitary design, right, can we prove anything about the complexity of unitaries drawn from that design? Right, and we'll get back to random circuits in a second. And the idea is basically, yes, designs are a very powerful concept, and you can essentially just prove a lower bound on the complexity of a unitary drawn from that design. So there's some distribution of unitaries. You take one, and what you can say is with extremely high probability, its complexity is roughly lower bounded by something linear in K. So you can just think about that as the complexity is linear in K. Okay? The n factors won't be that important for me. Right, so it's good. If you wanted the more precise statement, the statement is with probability exponentially close to 1. There's some lower bound on the complexity, but the important behavior here is that it's linear in K. The other factors don't matter that much as long as you're sort of studying sub-exponential moments in reasonable gate sets. Okay. Good. So yeah, just the point, what you should think about is complexity is going linearly in K. Right. Our original goal is to study the convergence of random quantum circuits to, or sort of how they're, the goal was to understand the circuit complexity of random quantum circuits, and now our goal is to understand how random circuits form unitary designs, because that'll tell us something about their complexity. Right. So the thing we're interested in, at what circuit depth we start evolving these unitaries. Right? Do we start generating K designs, and then we can say something about their complexity? Okay, so another sort of way of thinking about this is you can sort of think about random quantum circuits as some random walk on the unitary group. Starting out at the identity, they just sort of spread out this distribution of random quantum circuits of depth P spread out over the unitary group, and you're basically asking, sort of when do they spread out enough that they form designs, and then you can sort of infer something about their complexity. You sort of left low complexity subspaces, and you can prove that they must have high complexity. Okay, so basically this is also like a 12-year-old, 13-year-old subject. So it's been known for a while now that random quantum circuits form approximate K designs with some some polynomial dependence on K. And there's been sort of some work over the last few years to basically get that K dependence down to linear, which is actually what we need. And so sort of a conjecture for a while that random quantum circuits form K designs linearly in K. And yeah, there's a few different approaches where you can sort of generalize these 1D results to other architectures and sort of study cases where you're considering random circuits with fewer non-Clifford gates. But the important thing I need here is just that the scaling of depth is linear with the design order K. Okay, and the reason we want this is I told you that complexity is linearly dependent on K, right? We have this lower bound that depends on K. So if we can say that the time is linear in K, then we get linear complexity growth, which is what we want. Right? If I have some high degree polynomial in K, then I get some algebraic, sublinear growth. Yeah, please.
In the previous slide,
yeah.
the T is a log n.
Yeah.
But the complexity is like proportional to X.
That's right. I don't really care about the n factors. Yeah, yeah. The n factors might be architecture dependent. The important point here is I just want a linearly growing lower bound. I might miss some n factors. Yeah, I can talk later about sort of like improving some things to get better n factors, but they won't. You can sort of think about that as some n-dependent slope, and you obviously want the n-dependent slope of the lower bound and the upper bound to be the same. I think now we're only off by like a log factor, but I'm sort of sweeping those. I'm more interested in the linear growth. You can sort of think about n as some large fixed numbers. Okay. Good. So yeah. So before using this result from Brandau-Hara-Horodecki, which gave this t to the 11 or t to the 10 behavior, that gave you some complexity growth lower bound, and sort of over the years, this exponent was sort of, this polynomial behavior was sort of slowly improved. But I guess linear designs were sort of out of reach until last year. So there was basically a flurry of activity from like February to June last year. A bunch of papers came out, and there was sort of this beautiful synthesis of techniques involving really, really heavy machinery, and that sort of finally established that random circuits form designs linear in K. And this involved a lot of technical pieces under the hood or behind the scenes. Okay, right. So that's basically the story, right? Random circuits form designs linear in K. You get, that the design of, so the complexity of a design unitary is also linear in K. That gives you linear complexity growth for random quantum circuits. And that's sort of up to some polylog factors, proves this Brown-Susskind conjecture. Yeah, please. No. I like questions.
Like linear T, K, rate the complexity growing linearly at this function on time.
Yeah, so.
Can you repeat the question?
Oh, sure, yeah. I think the question was about was the question about exponential times or just about the linear behavior? Okay, so the idea is basically complexity scales linearly in K. You need T to scale linearly in K to get a linear complexity growth. If T scales worse in K, then you have some sublinear complexity growth, which is fine, but the goal is to prove linear complexity growth. And yeah, there's some subtleties which happen when you get to exponentially high moments. I won't really talk about those, but basically something caps out. You sort of, higher moments don't actually buy you much once you get to exponential moments. Yeah, sort of like, there's some like k factorial factors that sort of kill the complexity growth. That's a great question. Yeah, and I'll try and remember to repeat the questions. Okay, so that's sort of the intro part of my talk, which is fine because it was all the machinery I needed. You know, you could ask, where do we go now? And I think the interesting thing I want to sort of mention is that there's a lot of interesting states that are not pure states, and I think mixed states are a good sort of you know, I think asking about the complexity of mixed states is very interesting. And specifically, what I want to do is consider the complexity of subsystems. Okay, so with that story in mind, what I want to do is consider an n-qubit system, initially in some unentangled state, which undergoes some unitary evolution. This could be some random circuit or some Hamiltonian evolution. And I want to ask about the circuit complexity of a subsystem, okay? Some density matrix and some spatial contiguous subsystem A, some spatial subsystem. And ask about how the complexity of that subsystem changes in time. And, you know, the rough intuition is if I look at really big subsystems, that's probably somewhat, you know, tracking the linear complexity growth. And if I look at really small subsystems, somehow something should be trivial. And, you know, is there any interesting behavior or transitions there? Okay. And again, this is where holography sort of starts giving you surprising things. You know, basically complexity in holographic systems is some minimal surface. If you start changing things around, minimal surfaces can jump. And that's very surprising because, you know, it's sort of unintuitive that as I start changing, like the size of my subsystem evolving in time, that the complexity of my state could just jump discontinuously. So, you know, already sort of holography is making some surprising conjectures. So the complexity of an n-qubit density matrix, again, basically what I want to do is just sort of imagine the same thing, but I'm sort of allowing you to prepare some state on an n qubits plus a polynomial number of ancilla using gates comprised from some gate set, universal gate set of elementary two local gates. And then we're just going to say that a density matrix has some complexity if you can sort of take those states, trace out some degrees of freedom, and get a state which approximates the density matrix you're interested in. Okay, and then we're just going to take the smallest circuit which does that. So you can sort of think about this as take your density matrix, take all the states in a ball around it, take all their purifications, and then take the one with the shortest circuit complexity. And I think this is sort of operationally what we might mean by the simplest way of preparing that state, right? You have a bunch of qubits in your lab, you know, act with a few gates, and then throw away degrees of freedom, right? That may be the simplest way of preparing that mixed state. Okay. So again, what I'm going to do is to sort of study this problem more precisely. I want to consider NA qubit subsystems of n-qubit random quantum circuits. So I'm going to have some subsystem A, and I want to study the subsystem complexity in this model. Okay, so how the complexity of the subsystem grows. And I'll just define this sort of fraction. So NA will be some extensive subsystem. P will be the ratio NA over N. And I first want to consider subsystems greater than a half. Okay. So what you can do is, in this regime, you can actually prove that for any subsystem, you know, a fraction greater than a half, the circuit complexity just grows linearly up to some polylog factors. Okay. So you sort of use unitary designs again to sort of precisely control the moments of your density matrix. But the point is, you just sort of recover the same picture we had before. You get this linear complexity growth and this saturation of exponential times. Okay, and this happens basically for any fraction greater than a half. Okay, but now there's some more interesting features if you look at subsystems that are less than a half. And you know, this is old result. Basically, this is essentially known since the 1970s that subsystems of random states are extremely close to maximally mixed. Okay, and we can basically use that, you know, confirm that intuition. More precisely, we can just compute how the purity evolves in random quantum circuits. There's some nice mapping of the purity to like a random walk problem you can solve exactly. But basically, the purity is just exponentially decaying. Okay? And what that tells you is that at linear depth, your density matrix for less than half-size subsystems is close to the maximally mixed state. the maximally mixed state is an easy state to prepare, right? You just take 2n qubits, you know, make a maximally entangled state on those 2n qubits and throw away half your qubits. Okay, so this tells us that at least at linear depth, right, your state is simple. It doesn't really tell us what's going on before that, though. So, you know, naively, we just have these upper bounds for the complexity for less than half subsystems, where this is just the light cone of your subregion, and then at some point you have this complexity upper bound from, you know, your state being close to the maximum mixed state, which just kicks in at linear depth. Okay, so as I emphasized, the hard part is computing lower bounds. And what you can actually do is show, you can sort of use either log depth designs or some arguments involving the purity to sort of show, and there's some subtleties here that you can ask me about later, but you can basically show a lower bound which rises and falls, right? And importantly, it sort of rises above the late time complexity upper bound. So this tells you that the complexity of less than half size subsystems needs to grow and then fall. Right? So you're evolving your subsystem, that subsystem is becoming more and more complex, and then at some turnaround time, the state starts getting simple again. Right? So there's some time scale where your state goes from, you know, sort of becoming increasing complexity, and then it starts just sort of like simplifying itself as it entangles with the complement. Okay. Right, so that's somewhat surprising. But maybe just something to point out is I don't actually know exactly what's going on in here, right? This is a lower bound, this is an upper bound. The true behavior could be something where you sort of smoothly go up and smoothly go down, or the behavior could be something sharp, where you go down and all of a sudden, you know, you sort of enter some epsilon ball or delta ball around the identity and your state just immediately becomes simple. Sort of both are consistent with this picture. Okay. So we've already sort of seen one sharp transition, and there's something that happens sort of very discontinuously around half system sizes, where for any system, subsystem less than half system size, right, we get this sort of growth to sort of, you know, sort of n squared complexity, linear depth, and then you sort of, you know, approach the simple state. But if you look at any subsystem greater than a half, right, you get this, you know, long time complexity growth where the complexity saturation value isn't n, it's like 2 to the n. So there's some, you know, discontinuous transition around 1/2. Okay, and just to sort of give the picture from holography. Again, this is not a talk about holography, but I'm just using these sort of things to motivate studying subsystem complexity in many body systems. There are actually a lot of transitions that happen in holography. There's basically 3 that happen as you sort of change the size of the spatial region, and 2 transitions in time. And notably, for less than half system sizes, the complexity does drop sharply, right? So in holography, basically what you get is the complexity of your subsystem grows linearly in time, and then sort of instantly at some time scale, it just drops to something trivial. So sort of your state just sort of immediately becomes a simple state at some time. Okay. Yeah, there's also this prediction from holography that there are subsystems where the complexity never grows. So this is a surprising prediction from my point of view from many body physics, because it's saying that if you look at small enough subsystems, so, you know, some extensive but small enough subsystem, somehow the state's always simple, you know, as long as you evolve it, which seems very surprising. Importantly, this critical subsystem size here, below which you can the complexity growth is trivial, depends on the sort of temperature you equilibrate to locally, and for random circuits, you sort of are always at infinite local temperatures, so this p crit is actually 0. But you know, for some Hamiltonian evolution, where you reach some Gibbs state locally, this seems like it's implying that there should be subsystems which are always trivial. Okay, so this is my last slide. Yeah, I think all of these sort of behaviors, there's a lot of like open questions here. And specifically, this is one that that we still don't really understand. Is like, what does this complexity collapse look like in random circuits? You know, is the complexity growing and then decaying sort of smoothly, or is it growing and then just sort of suddenly crashing down? And you know, sort of one conjecture we might make is that at least if you take the local dimension to be very large, right? Basically, when you do that, the time scale that you actually reach the maximally mixed state sort of goes to NA over 2. Which is precisely the time scale where this lower bound stops. So somehow your lower bound and your upper bound meet if you take Q to be very, very large. So, sort of you're making this window very, very small for your complexity, and you might believe that that sort of is implying that something maybe has to drop pretty sharply in the large Q limit. Also sort of like, holographic systems in some sense have many degrees of freedom per site, so maybe this is somehow the correct holographic limit, because indeed this is the picture you see in holographic systems. No, yeah. So I haven't, everything was qubits before. Now just for qubit systems, yeah, just on this one slide, if you were to take random circuits, make your local Hilbert space dimension something larger Q, and then took that to be large, maybe this is the picture you see. Everything I said before is all for qubits. Okay. So that's it. I think this is sort of an interesting problem. I think this is sort of a richer picture than normal complexity growth was sort of painting before. And I think sort of interestingly, there are all these behaviors that, holography is predicting that we don't know how to see in random quantum circuits. And I also think it's sort of interesting, we could just imagine, adding noise to our system, adding measurements to our system. Can we prove sort of complexity lower bounds? Are there interesting transitions as I tune the measurement rate or tune the noise rate? I think these are all interesting questions. But I think, I'm now out of time, so I'll end there.
Maxim?
Can you predict sensitivity of this picture to dimensionality of the system from holography, or do you expect any qualitative changes as spatial dimensions change?
Oh, good. In holography, there are some dependencies on the spatial dimension. I don't know how to see any of those in random circuits. Everything in random circuits seems very agnostic to the architecture. But yeah, sort of this critical size below which your complexity growth is trivial depends on the local temperature, but it also depends on the sort of spatial dimension of your system. But random circuits seem to not know about that at all. So somehow, yeah, the picture that this is sort of conjecturing for many-body systems seems a lot richer. Yeah, so I don't. Good question.
So I first have a comment. Mm-hmm. So could you go back to the last slide with that shape? Mm-hmm. Yes, exactly. So I don't know too much about this notion of complexity, but there's an obvious notion of complexity for the reduced density matrix. Mm-hmm. That is to view it as a state, and then look at its entanglement between subregions. And so if you do that calculation in random circuit, you will get a similar shape as your blue curve, and it will have certain
but that's as I tune the subsystem size, right?
You can tune the subsystem.
No, but there the transition happens around like half system size. You mean this like page curve?
No, it's not page curve.
You mean something in time?
It actually has 3 segments. Yeah, there's a linear ramp, and then there's a plateau, and then it goes down to 0. Exactly for the same reason that when you have subsystem.
But as a function of time.
As a function of time. Yeah. So there's also a corresponding holographic picture, which is supposed to map to the reflective entropy. And so So I'm not sure whether it corresponds to the curve that you're looking at, but there seems to be a similar behavior.
Yeah, in some sense, this needs to be related to the entanglement, because your subsystem being close to like maximally mixed, you can use to lower bound the entanglement and say that your von Neumann entropy needs to be close to maximal. Yes. I'm not sure what how it would be related in the middle there, but I imagine that there's some precise correspondence that can be made. But I did think about it, and I couldn't actually figure out a way to use the entropy to bound the complexity. So yeah, the precise connection, I'm not sure.
So the question I have is that what is the holography picture that you use? What is the corresponding quantity that corresponds to this complexity?
Right. So this is in a two-sided geometry. These are subsystems. So you take a subsystem on each side, and you're just asking about the minimal, given those two subsystems, what's the minimal surface in the bulk? That's the picture. Right? So basically, if you take them to be very large, the minimal surface is something that extends through the geometry. But for less than half system sizes, if you make the geometry bigger, it sort of like discontinuously like jumps down to something that sort of doesn't connect the two regions through the geometry, just connects them locally. But it's sort of like the complexity of subregions in the thermal field double state.
I see. Okay, thank you.
Yeah.
Thanks for the very nice talk. I was wondering about the status of these conjectures in this Q to infinity limit. I mean, my impression as an outsider was that you can make these statistical mechanics mappings exact.
Yeah.
So is it then easy to prove these things? Or?
I don't know. Yeah, there's nice stat-mech models. All the approach, right, so you sort of need to control complexity with something. One obvious thing to control it with was like moments of the density matrix. Those didn't seem like they, as you take Q to be large, to really, yeah, sort of what you want is the peak of this lower bound to move as you take Q to be large. If it moves this way, that tells you something is happening more sharply. Everything seemed agnostic that I tried, at least, to the local dimension. So this was like doing stat-mech mappings for like the moments of your density matrix. Like none of that really seemed to work. But maybe there's just some, maybe that like the quantity I'm considering isn't capturing the picture, and there's something which more directly like sort of sees the complexity of behavior, and if you take Q to be large, sort of moves over. Yeah, like Zhongwan's paper sort of had a different idea in using the mutual information, and he was more confident that as he took Q to be large, he could see something sort of move over, but I think, you know, the picture also wasn't clear to me.
Okay, thanks.
Yeah, good question.
Thanks for the very nice talk. Yeah. I was wondering about the definition of the mixed state complexity. You can imagine a different definition where you take pure state decompositions.
Great, yeah.
Like, do you expect the
I have no idea. Yeah, I like that a lot. Like, there's sort of the one I took was more operational. This is sort of like maybe what you mean by like the easiest way to prepare some mixed state. If you just have like, you know, a bunch of ancilla qubits and you're acting with like local gates and throwing away qubits. But yeah, I like this idea of like fix some basis or something. What is the sort of the smallest statistical mixture? Sort of, yeah, I like that a lot. I have no idea what the picture would be like. But yeah, I think you would imagine a lot of different definitions of the complexity of mixed states, and maybe there's some, you know, very different behaviors for all of those.
Yeah, thank you for the talk. Just wanted to know if something is known about the complexity of, like, the hardness of finding the optimal circuit, right? So even if you know that there is some, I guess it's even more difficult.
Yeah. These are all, that seems extremely hard. Yeah, I think, and sort of, yeah, I think if you had an efficient algorithm for doing that, that would imply very scary things in complexity theory. I think you'd collapse a lot of complexity classes if you had an efficient way of doing that for general unitaries. Yeah, sort of, the statements I'm making are much weaker in the sense that they're sort of proving probabilistic lower bounds on the complexity, but you can never sort of point to a specific unitary and explicitly sort of construct some minimal circuit. Yeah, that seems like a very hard problem. But I mean, you know, maybe why this picture is sort of interesting is that at least like, say you have some density matrix and you thought the complexity was something, but you know, proving these bounds that sort of really say that the complexity is trivial, that implies that there's going to be there's some better representation for that density matrix that you might not have known about. So I think sort of the you know, complexity of mixed states is still sort of painting some interesting picture for, you know, when states are actually hard versus easy.
Hi, thank you for this talk. So as experimentalist, I have really simple questions. So like for our community, I sometimes ask myself like whether our community, by using synthetic quantum system like optical lattice, static quantum dynamics of many body systems, has shown some quantum advantages, like maybe already 10 years ago. But I think the answer to that, people may have different opinions. So I just wonder whether your study can provide some insight into that. But one big difference I could see in this random quantum circuit, maybe the temperature kind of go to infinity at the end, which may make the system kind of trivial maybe at the end. So I wonder how could we do some like confined temperature and have a Hamiltonian and understand for what type of Hamiltonian the quantum dynamics is a hard complex.
Yeah, I'll say that most quantum advantage experiments are specifically, at least the ones we normally think about as sort of, at least in the computer science community, is maybe more about like sampling problems, which are sort of related, you know, you have some output distribution and you're sort of saying that the sampling task, sampling from that output distribution is hard. I don't think that precisely relates to sort of circuit complexity. But maybe more to your point, I think it's still, you know, I still like to understand this story for like Hamiltonian systems. I think there's probably a richer picture of like what the complexity of Hamiltonian evolution is doing, and you sort of roughly expect these features. I don't know if I really answered your question.
Just to confirm, so it's still ongoing research in the context of Hamiltonian.
Oh yeah. I mean, I think all of the things you really want to understand about complexity growth are all Hamiltonian systems. I think I think we now basically have proof techniques for proving circuit complexity lower bounds that work for any time-dependent system. I think we know embarrassingly little about how to prove, it's sort of, like Robert's talk was also somewhat related to this yesterday. I think there's very little we know how to prove sort of about like, the complexity or hardness or sort of like the types of distributions you get on the unitary group from Hamiltonian evolution. So yeah, I think there's a huge number of open questions there, and even the definitions aren't really clear.
Thanks.
Pablo, please make it short, and while Guido set up the next talk.
Then it was, okay, I can ask like, so quick question, do you have any clear upper or lower bounds for complexity that one can compute numerically? So something that's clearly related, or a clear probe?
Good, yeah. So maybe one thing I'll say is you could ask, are there are there other quantities that like many body physicists like to think about that it's sort of like track complexity growth and maybe more natural, like entropies or observables. And I think that there are sort of avatars of complexity growth in the distribution of entropies of your subsystem. So I think if you, and again, all of these things are going to be like sort of very hard to compute numerically. I think, there's sort of like a few sort of things you can maybe compute that sort of track what the complexity is doing. But I do think that like somehow, like as you time evolve, I think there's the picture of what your entropies, subsystem entropies are doing is much more complicated than just they equilibrate. I think if you think about some like distribution of systems, that sort of distribution of subsystem entropy sort of keeps changing for very long times, and I think that is related to complexity growth. So I think if you sort of like make histogram plots of subsystem entropies for your favorite class of many body evolutions, that sort of knows about complexity growth.
Thank you.
I don't know if this is a satisfying answer or not. Yeah.